In this video, we will discuss the motion in 2 dimensions and in 3 dimensions, following our discussion on the motion in 1 dimension in chapter 2. So again, in this case, when we describe a motion of a given object, whether in 2 dimensions or 3 dimensions, we will need the basic variables required to describe this motion, which are the position, the velocity, and the acceleration. In this case, we'll focus more on the vector nature of the position, the velocity, and the acceleration, because each of these variables, whenever the object is moving, will have more than one component, because the motion is happening in more than one dimension, in contrary to the previous case, which was motion in 1 dimension. So what we are going to do in this chapter, the following. We will start by defining the position, velocity, and the acceleration in case of 2-dimensional motion. And in the second step, we're going to actually discuss some particular cases of a 2-dimensional motion, which are the uniform circular motion and the projectile motion a priori. So whenever we want to describe the motion of a given object, whether in 1, 2, or 3 dimensions, doesn't matter. We all know by now that we need the position. So it's the basic and the most fundamental variable that we will use to define all the other variables. So consider that you have a particle that is moving in a space. We represent this space by 2 axes, which is the x-axis and the y-axis. And let's say that at a given time t, the particle is found at a given point A. So the point A, it represents the position of the particle. Now, how can we write down this in a mathematical equation or in terms of mathematical objects? What we do is that we take the projection from the point A, the location of the particle, onto the x-axis. And by this, we would have, the x coordinate of this particle. So we'll have, let's call this xa. So xa is the x component of the position of the particle at point A. And if you make the projection from the point A onto the y-axis, then this would be nothing else than the y component of the particle at the point A. So let's call them xa and ya. Therefore, you have 2 components that describe or that precise or that defines the position of the particle at the point A. So all what you need to know now is to put all this information together. And how do we do this? Actually, we do this through the position vector. So this is the position vector of the particle A. If I just put here an index A, then RA would be equal to XA I plus YA J, where actually I and J are the unit vectors of the axis X and Y. And so the vector R is drawn as the line that connects O, which is the point of reference of this system of coordinates, to the point A. So this line between O and A is nothing else than the vector position RA. And so this is how we define the vector position of a given particle in the case of 2-dimensional motion. Now, we have defined the position. Now we need to move on to define all the other variables. But to do this, first of all, we need to define what is the displacement in this case. So let's consider a motion, a 2-dimensional motion of a particle in the XY plane, as we have seen earlier. So this is X and this is Y. And let's say that we are actually monitoring the motion of the particle between 2 positions, the initial position at point A and the final position at point B. So what would be the displacement in this case between points A and B? It's very easy. We have seen previously that the displacement is, first of all, a vector. This vector is defined as the difference between the position of the particle between the final time and the initial time. So we expect that delta R is equal simply to R final minus R initial. This is it. This is R final minus R initial. So R final is the position of the particle at point B, and R initial is the position of the particle at point A. So how can we write this in terms of the components X and Y? Actually, it's very easy. So look, R final is nothing else than X final I plus Y final J. And R initial is given by X initial I plus Y initial J. Now, if we put all the variables that are on the same axis together, so if we put X final I and Xi I together, we'll end up with X final minus X initial. This difference between the two variables is along the x-axis because they both have the unit vector I. And then we can write down plus Y final minus Y initial along the y-axis, so it is times J. And we can actually call these two differences. So this first one, we can call it delta X because it's the difference in the X position of the particle between the final time and the initial time. So we can write this as delta Xi plus, this can be written as delta Yj. And so we can write down actually the vector delta R as we can see in here. It's the sum between delta Xi plus delta Yj, where delta X is the displacement along the x-axis and delta Y is the displacement along the y-axis. Now, the vector delta R is the sum of these two components, delta Xi plus delta Yj. And the way actually we draw it is we start from the initial position and then we draw a line from the initial position to the final position. And this line would define the vector delta R. So of course, positive and negative signs are no longer sufficient to determine the direction of delta R. So previously in the case of motion in one dimension, we used to say that if delta R is positive and if delta R is negative, this is enough to tell us in which direction the particle is moving. So either it's moving in positive X direction or is it moving in the negative X direction. But here, this is not enough. It's not any longer the case because the particle is not moving along one axis, but it's moving in the XY plane. So we will need actually to use the full vector notation of the displacement vector delta R. And this is why we're gonna use delta R equals delta Xi plus delta Yj as the definition of the vector displacement. We move on with the average velocity. So once we define the vector displacement, now we can go to define the velocity. And here we can actually define two types of variables for the velocity. First of all, the average velocity and then the instantaneous velocity. And we are going to use the same reasoning as we have used for the case of a motion in one dimension. So the average velocity is defined as the ratio between the displacement to the time interval for the displacement. Or in other words, the average velocity, it defines the rate at which the position is changing in a given time interval. So if we take again the same example in here, so we have the particle moving in XY plane between two initial time Ti and final time Tf, so between the position A and B, then we define the vector average velocity equals to the ratio between the displacement vector delta R and the time interval delta T. So the average velocity, as you can see here, is directed along delta R because since delta T is a scalar, so it's just a number, right? This means that the V average is equal to delta X over T I plus delta Y over delta T J. And so as you can see, the direction of V average is the same as the direction of delta R because you have the same delta Xi plus delta Yj in the expression of V average. Also, the average velocity between two points, in this case A and B, is independent of the path taken between these 2 points. So as we have discussed also in the one-dimensional case, the average velocity does not depend on the path that is followed by the particle or taken by the particle to go from initial position to final position. It only depends on the initial position itself and the final position. So V average depends on delta R, because it's actually proportional to, it's equal to delta R over delta T. And delta R, it has two components, delta Xi plus delta Yj. And it depends on the difference between the positions. So it equals X final minus X initial I plus Y final minus Y initial J. And as you can see from its expression, it has nothing to do with all what happens in between the initial time and the final time. It only depends on the difference between the initial and the final position. Okay, whenever the particle moves from XA, XI to X final through different X, so it could be between X initial and X final, we'll have, for example, the particle moves through X1, X2, X3, etc. up to X final. So these X1, X2, X3, all the intermediate steps that the particle follow between X initial and X final do not enter into this expression. And this is why the V average, it only depends on the points, the initial and the final points, and it is independent of the path taken between the 2 points. And finally, if a particle starts its motion at some point and then returns to the same point, then its average velocity is 0 for this trip, regardless of the path taken by the particle. So again, if a particle starts moving at point A, so for example, let's say here's the point A, here the particle starts moving, then it just follows some arbitrary path going from A, and then it gets back to A. In this case, delta R is equal to 0 because it's equal to R final minus R initial, and H final is equal to R initial. So delta R is equal to 0. And if delta R is equal to 0, it means that the average velocity is equal to 0 as well. So that's concerning the average velocity. Now, we want to define the instantaneous velocity. And we know that the instantaneous velocity is the rate of change of an object position at a given time. So as we have done previously, we are going to define this instantaneous velocity on the basis or using the definition of the average velocity. We have seen that if you take 2 points at different instants, so T initial and T final, that defines the time interval, the average velocity is defined as delta R over delta T, and delta R is the line that connects the initial point to the final point. Now, whenever we talk about the instantaneous velocity, we actually want delta T, the time interval, to approach 0. And when delta T approaches 0, that means that the vector B is the point B is approaching A, which means that the delta R, the vector delta R, that connects the 2 points A and B, its direction will approaches the direction of the green line that is over here. And the green line is nothing else than the tangent to the curve at point A. So from here, we can deduce that. So if you just let the point B move along this curve, and at each point you will draw its delta R vector, so the difference between the position, the initial and the final position, you will see that at some point, as long as B approaches the point A, and therefore as long as delta T approaches 0, this vector delta R at the end will end up with this green line. And this green line is simply the tangent to the curve at the point A. So this is why we define the instantaneous velocity as the limit of the average velocity when delta T approaches 0. So we take the definition of the average velocity, and we say that the instantaneous velocity is the same, however, when delta T approaches 0. So when you take the limit of this expression as delta T approaches 0, you end up with the derivative of the position with respect to time. And from here, we can define the instantaneous velocity as the derivative of the vector position with respect to time. And this is what you need to know. Here it is. So we have defined the average velocity as the ratio between delta r and delta t. And we have defined the instantaneous velocity as the derivative of the vector position with respect to time. Now, the direction of the instantaneous velocity v at any point in the particle's path is along a line tangent to the path at that point and in the direction of motion. As we have discussed in this point in here, whenever delta d approaches 0, the direction of delta r actually will be the same at the point A as the direction of this line tangent to the curve at point A. And we are going to generalize this conclusion to say that if you take any point along this curve and you want to know what is the instantaneous velocity, all what you need to know is to draw a line tangent to the curve at that point. So let's call this point C. The line tangent to the curve at the point will be the instantaneous velocity v, and the direction or in which direction you will draw this this vector v, it's going to be in the same direction as the motion, right? So if you draw first the line, or if you take another point like in here, so the particle, let's say it's moving in this direction, so it's moving like this on this curve. If we want to define how much, or we want to draw the instantaneous velocity at this point. So first of all, we draw the tangent to the curve at this point, and then we see in which direction the particle is moving. So you can see that the particle is moving in this direction, so in the opposite direction with respect to x at this point. So this is why we are going to draw a vector like this. So this vector is along the tangent and in the direction of motion of the particle. And this would be, so if you call this point D, then this would be the instantaneous velocity at point D. So this is it for the velocity. Let's move on with the acceleration. Again, we consider a particle moving in the XY plane from a given initial position A to a given final position B. The average velocity of the particle, it defines the change in its instantaneous velocity in a given time interval. So if you look at the particle at these two different points, let's actually define each variable at each position. At the position A, the vector position is defined by Ri, right? So we have here, we call this initial time, the time at which the particle was at point A, and time t final is the time at which the particle was at point B. So at the point A, the particle is defined by, the position of the particle is defined by the vector Ri, and it has a velocity Vi. As you can see here, it's drawn with this red vector. And at point B, also we can define both the vector position, Rf, and the vector velocity Vf. And please note that these two variables which are written here, V initial and V final, they correspond to the instantaneous velocity. It's the velocity, Vi is the velocity determined at the time Ti at the point A, and V final, Vf, is the instantaneous velocity evaluated at the time Tf at point B. Now, the average velocity determines how much this velocity is varying in a given time interval, and this is why it's simply the ratio between V final minus V initial divided by the time interval T final minus T initial. And the direction of A average is mainly and essentially given by the direction of this vector V final, the difference in the vector V final minus V initial, or what we have called delta V. Okay, so how we can draw this difference between the two vectors V final and V initial, we can see it in here. Actually, so we have said that the average acceleration, the direction of the average acceleration is defined by the direction of the vector delta V. And delta V is nothing else than V final minus V initial. So we know how to make a addition of two vectors. So this is why what we are going to take is the following. So this is our graph where we have V initial and V final. If you just take V initial, we have just taken V initial and put it in here. And we have conserved its direction. And this is the vector V final. Now, we can write down delta V as V final plus, so we add to V final the vector minus VI, right? Now, we have VI and we have V final. So all what we need to define is minus VI. And as you can see, minus VI is simply VI, but in opposite direction. You change the direction. So this is why if you change the direction of VI, you end up with a vector minus VI, right? And then all what you need to do is to make just an addition of vectors. So here is our vector VF, and then you add to it minus VI, and you end up with the direction of the vector delta V. So between point A and B, the direction of the vector A average is nothing else than the direction of this vector delta V. So this in case you need to understand a graph and you need to extract some information out of a graph, you will know that actually this is the way we draw delta V, and A average, the direction of A average is defined by the direction of delta V. So this is it about the average acceleration. Another variable of interest is the instantaneous acceleration. And the instantaneous acceleration, it gives us the rate at which the velocity is changing, is varying with time. So this is why it's simply the derivative of the vector velocity with respect to time. And so as you can see from this expression, the acceleration depends on the variation of the velocity. So this may occur in different forms, either as a change in the magnitude of the velocity, because don't forget that since V is a velocity, then it has two things. It has a magnitude, as we all know, for all vectors. Any vector, it has a magnitude and it has a direction. Okay, so the variation of the vector velocity could be as a change in the magnitude, like in this case. It could be as a change in the direction. And in this case, you could have also the magnitude constant. And it could be both of them. So either you have a change in the magnitude of the velocity while the direction is fixed. You could have a change in the direction of the velocity while the magnitude is fixed. Or it could be that both the magnitude and the direction are changing as a function of time. And we are going to see some examples on these different cases. So let's start first by the first application, I would call it. In this application, we will study the dimension of a given particle the motion of a given particle in 2 dimensions under constant acceleration. So we have seen this case in the 1-dimensional motion, and we have actually derived all the kinematic equations that describe the motion. And we have seen that we can write down x, the position, as a function of time, the velocity as a function of time, and the velocity as a function of the position and the acceleration. So what we are going to do here is to write down these equations for the case of 2-dimensional motion, okay, and under constant acceleration. So the strategy we can follow is the following. We can think of this as, of this motion as 2 independent motions, okay? Each one is happening in a given direction perpendicular to the other. So we can think of it as 2 independent motion. The first one is happening on the x-axis, and the second one is happening on the y-axis, which is perpendicular to the x-axis. And actually, any influence in one direction does not affect the motion in the other direction. So in other words, these 2 motions, they are completely independent. So we are not going to derive this kinematic equation, but we are going to actually conclude them. We are going to get them out of the 1-dimensional motion. So I would recall you here. So we have here 1-dimensional motion. We take it to be along the x-axis just as an example, but it doesn't matter. And in this case, we have defined the position as x, the displacement as delta x, the velocity, we have written v in this way, and we said that this is a vector along only one dimension, so we have taken to be vx. And then we have written these two equations of the velocity and the position versus time. Now, in the case of two-dimensional motion, we also can repeat the same exercise, and we can define all these variables. So in this case, instead of x, we will have a position vector r, which has two components, both x along the x-axis and y component along the y-axis. The same way for the displacement, instead of delta x, we'll have delta r. And delta r, again, it has two components. It has delta x and delta y. The velocity vector is no longer just one component, but it has two components, vx and vy. And now we go to the kinematic equations. So here, instead of having one equation, which is along one axis, we will have the same form of the equation, but we will not forget that v0 is a two-dimensional vector, a is a two-dimensional vector, and v is a two-dimensional vector. So this is the kinematic equation for a particle moving under constant acceleration in two dimension. And if we want to actually expand this equation, you'll see that it has two equations hidden. The first one, if you project this equation along the x-axis, you'll find that you have the x component of the velocity is equal to the x component of the initial velocity plus the x component of the acceleration multiplied by time, and the same for the y-axis. So we'll end up with vy equals v0y plus ayt, where v0y is the y component of the initial velocity, and ay is the y component of the acceleration. Also for the position as a function of time, which was the third equation, with the second equation we have derived in there, you can see that we have in this case, we had actually x equals x0 plus v0t plus half at squared. So we can generalize this expression and write it down as a two-dimensional equation where the r vector is equal to r0, the position is equal to initial position plus v0 times t plus half at squared. But instead of having simple variables, because they are defined along one dimension, we will have them written as vectors. And again, if you project this equation onto x-axis and the y-axis, you end up with these two equations. X equals x0 plus v0 xt plus half axt squared, and y equals y0 plus v0 yt plus half ayt squared. So this is concerning the case of two dimensions or two-dimensional motion. What if the particle is moving in three-dimensional motion? So in this case, you will have actually one more variable. So you will have x, you will have the y axis, and you will have, in addition, the z axis. So you will have three coordinates instead of only two. And so we can simply update this equation by adding to the equation, to each equation actually one component along the z axis. So for the position, you will end up with xi plus yj plus zk, and the same applies for all other equations. And so these equations, we have to know them, and then we can immediately use them in the applications. We continue with the uniform circular motion. So uniform circular motion is a very interesting and famous application of two-dimensional motion. And actually, uniform circular motion, it occurs when an object moves in a circular path with a constant speed. That means that the particle is moving along a circular path, and the magnitude of its velocity does not change as a function of time. So here we have an example that illustrates this figure that illustrates this example. So as you can see here, that the vector velocity in this kind of motion, which we call uniform circular motion, it has a constant magnitude. So if you draw the velocity vector at different points, we have seen previously that if you take any point along a path followed by the particle, and you want to draw the instantaneous velocity, all what you need to know is to draw the line tangent to the curve at that point, and then to specify the direction of the vector in the same direction of motion. So if you call this point M, for example, then we can say that this is the vector Vm. Now, the point is that along this trajectory, whenever you draw this velocity vector, so whether at point A, B, C, D, or E, the direction of the velocity changes. However, the magnitude is all the time the same. So this is why we can write down that the magnitude of the instantaneous velocity at point A is equal to the magnitude of the instantaneous velocity at point B, etc. However, this velocity, it always have a changing direction. So if you take any 2 points along this trajectory, you will have two different velocity vectors, in the sense that these two vectors don't have the same direction. And another point is that this velocity vector is all the time tangent to the object's path, and it's perpendicular to its radius. So at any point you take along this trajectory, and if you draw the vector, you'll see that this vector is tangent to the path, so it's tangent to the curve at this point, and it will be actually perpendicular to the radius. So if you just draw the radius between the point B and the center of the circle, you'll find that this vector is perpendicular to the radius. So in this case, actually, what happens is the acceleration occurs because we have a change in the direction of the velocity of the particle, and we don't have a change in the magnitude of the velocity of the particle. So this is, for example, what we have said in here. We have said that an acceleration can be different than zero because we have a change in the direction of the velocity of the particle, even though its magnitude remains constant. So for example, this is one of the cases, which is a uniform circular motion. So this type of motion is recognized as an analysis model. So in other words, you can find this model in different problems, and it is called particle in uniform circular motion. And the word uniform, it actually refers to the fact that the particle has a constant magnitude of the velocity along this trajectory. Another variable that we need to define whenever we talk about the uniform circular motion, which is of interest, is what we call the centripetal acceleration. So whenever you have a circular motion, you can always define a vector acceleration that we call a centripetal acceleration. It's called like that because this acceleration all the time points toward the center of the circle, and it is perpendicular to the path of the motion. So at any point, you can define a vector velocity v, as we have said earlier, and you can also define an acceleration, centripetal acceleration, and this acceleration all the time points towards the center of the circle. So it points towards this center in here, and it is actually perpendicular to the curve, which means that AC and V, they are perpendicular. The direction of the centripetal acceleration is changing all the time because the velocity has an always changing direction. And at any point, it is directed towards the center of the circle. The magnitude of this acceleration is given by AC equals V squared over R, where V is the instantaneous speed. And in the case of a uniform circular motion, this value is constant. So AC is also constant, it has the same value on all the points. And R is the radius of the circular path. So this is all what we need to know about the uniform circular motion, in addition to one more variable, which is the period. So actually the period is defined as the time needed for a particle to complete one revolution, to make one complete circle. We talk about this variable when we talk about the uniform circular motion. So the speed of the particle would be the circumference of the circle of the motion divided by the period. As you know, the speed is defined by the distance divided by traveled by the particle divided by the time interval. So we can say therefore that V is equal to the distance traveled in this case is the circumference of the circle, and the circumference of the circle is defined by 2 pi times r, the radius, divided by the time needed to complete this circumference is what we call the period t, so capital T. So we end up with this expression, and therefore from here we can define the period t as equal to 2 pi times r divided by v. So this period is defined in here, and we can actually memorize it to apply it, to use it immediately in our applications. Now, what about a more general case? So a uniform circular motion is a particular case of a two-dimensional motion. We can have a particle that is moving along a curved path. So instead of moving along a circular path like we have seen earlier, it could be moving actually not on this circular path, but it could be moving along a curve, and this curve could have different curvature, right? So what would happen in this case, and how can we describe the motion of this particle? So first of all, what we need to know is that if a particle is moving along a curved path, then the velocity could change in both direction and magnitude, which was not the case of a uniform circular motion. In the case of a uniform circular motion, a particle has an always varying direction as a function of time, but it has the same magnitude of the direction. Now, when we deal with motion along a curved path, both the direction and the magnitude would change. And in this case, instead of describing these variables in terms of x and y components, it's much better to describe them in what we call the polar coordinate system than in Cartesian coordinate system. What do we need in this case? Actually, we need two axes. Just instead of x and y, we will have two axes, r and t. So for the first axis, which we call the r axis, this is what we call the radial direction. So it's direction along the radius of the curvature of the path. It's defined at each point. So we're going to see a figure later on. So whenever you are at a given point, okay, you have the radius of this curvature. So here we have a curvature, as you can see, and the r direction is the same direction as the radius of this curvature, and it points outward. So it points towards the, not the center of the circle, but it points out of the center of the circle. And you have another direction, which we call the tangential direction. So this direction is tangent to the path of the particle. Now, as we know that v is along the tangent to the curved path from our previous slides. So this is why v is all the time along the tangential direction, and therefore it's perpendicular to the radial direction. So as you can see in here, so here's another example of a curved path, which is a little bit more elaborated, because in this case, you can see, for example, this is the path of the particle, right? And when we were saying actually different curvature of the path, this is exactly what we meant. If you take any point along this path, okay, you can define a curvature. And how this happened, actually, we consider that the infinitesimal displacement, so whenever the particle is a given point, you just take a small interval of this motion, and you suppose that this part, small part, is an arc of a bigger circle of a given radius r. So this is why here at this point you think that, or you assume that this part of the motion is an arc of this circle of radius, let's say r1. If you take another point, like in this point in here, we assume that this small interval is actually an arc of a circle, which is this one, of radius, which we call it the curvature radius r2, for example. And at any point, you would do exactly the same to define the radius of curvature. So whenever we're dealing with a curved path, we will actually need to define two components of the acceleration, a radial component and a tangential component. The acceleration, therefore, it has two components. AR, which arises from a change in the direction of the velocity vector. And this is AR. So AR, it's responsible for the change in the direction of the velocity. And this is why it points inward. So basically, AR is the same as AC in terms of magnitude. And A tangential, which arises from a change in the speed of the particle. So because the particle is changing its speed, so either it's increasing or decreasing. Whatever happens, this AT, it occurs because the speed of your particle is changing. And of course, AT is along the tangential direction. Now that depends on, depends AT if it's positive or negative, whether your velocity or speed or the magnitude of your velocity vector is increasing or decreasing. So that depends on different cases. But overall, we can say that the acceleration vector is the summation of two components, the radial component and the tangential component. And if you want to draw the A vector, all what you need to know is to sum up these two vectors, and on a graph, this is how it's done. So this is why you end up with this vector A, total vector A, which you can define at each point along this curved path. And here you have some more details about these components. So let's start with the radial component. The radial component, it has the same definition and value as we have seen for the centripetal acceleration. So AR is equal to V squared over R. And you have here a minus sign UR to say that AR is pointing inward. So as you can see in here, the radial acceleration, as we have said, is the direction that points outward along the radius of the circle. So this is why here you define it as pointing outward. And if you want to put here, or just you want to draw the unit vector, this would be the unit vector UR of the radius direction. So as you can see here, AR is in opposite direction with respect to R. So this is why we can write that AR is equal to minus some value along the radial direction UR. And this value is nothing else than V squared over R. So this is why here AR is equals to minus V squared over R UR. So you just have to keep in mind two things. AR, it has a magnitude V squared over R. And AR all the time points inward towards the center of the circle, okay? The tangential acceleration now, tangential acceleration is defined by the derivative of the velocity with respect to time. So since the velocity, the magnitude of the velocity is changing as a function of time, that means that we can define its derivative. And this is how we can define simply AT. So if the velocity is increasing, that means that dVdt is positive, and so AT in the same direction as the tangential direction, and the opposite in the other case. Now, the total acceleration can be defined as A equals to AR plus AT as a vector, and the magnitude of it is nothing else than the square root of AR squared plus AT squared. So the direction of the velocity would be the same as in the direction of the acceleration would be the same as the direction of the velocity if the velocity is increasing. If the speed, so the magnitude of the velocity is increasing, and it would be in the opposite direction with respect to velocity if the magnitude of the velocity is decreasing. So let's see here more a concrete example, which is a summary example. So let's consider this curve path, which has, and we are looking at different points actually along this curved path. So you'll see here, for example, if you take the point A, then we assume that this part of the motion is an arc of a large circle that you can see here in blue at the point A. And so what do we have? First of all, at each point, we know that we have two components for the acceleration, AR and A tangential. So we know that in here, the radial acceleration is all the time pointing inward. So it points towards the center of the circle, which we think the point A belongs to. And this is why we draw AR inward. And for the tangential acceleration, so we have seen that the tangential acceleration is given by the derivative of the speed, so the magnitude of the velocity with respect to time. And it is directed along the tangential direction. So how to draw it? Actually, it's very easy. The particle is moving in this direction, right? So at this point A, the particle is going down. And when the particle is going down, its velocity is increasing. So that means that A tangential is positive, and so A tangential is the same direction as V. So as you can see, V is in this direction in here, because V is tangent to the circle. At any point, V is tangent to the circle. So since V is increasing, then AT is positive, and so it is in the same direction. Now, if you look at the point B, for example, so again, at the point B, AR points towards the center of the circle that the point B belongs to, which is this big circle in here. If you want to draw the tangential acceleration, so at this point B, the particle, so as we said, it's moving in this direction. So the velocity vector is a tangent of the tangent to the curve at the point B. And so this is the vector velocity VB. Now, the point here is moving up. And so since it is moving up on a curved path, then its velocity decreases. And if the velocity decreases, we know that the derivative of U with respect to time, it's negative. And that means that the tangential acceleration is opposite. It has direction opposite to that of the velocity at the point B. And so after that, you just have to add up the two components to get the A vector. And at the point C, we just exactly apply the same reasoning. So we first of all define, so we draw this curved, we think that this part of the motion is an arc of a bigger circle. And so this is the circle for to which belong the particle C, right? So as you can see, it's a very big radius of curvature. So this point in here, we can draw two things. So first of all, the the radial acceleration that points towards the center of the circle. And we have the tangential acceleration. And again, if you draw here the velocity, here is V at the point C. The particle is going down, so V is increasing. So therefore, dV dt is positive, and so AT points in the same direction as V. And you can finally reconstruct the total vector acceleration A. So this is an example of a bigger circular path where you have different points and you have different parts. And as you can see, you can, in each point, you can define a different circle with a different radius of curvature. So this is it for this chapter. We will end up with the circular motion, and we'll move on to the applications.